This theory could change everything we think we know about reality, space, and time. New data from the James Webb Space Telescope actually suggests that our entire universe might be the interior of a gigantic black hole. From spinning galaxies to monster black holes, wormholes, and white holes, today we're facing a real cosmic existential crisis. Welcome, everyone. Black holes are among the most fascinating and mysterious objects in the cosmos. If these cosmic mysteries captivate you as much as they do me, why not hit the subscribe button right now? It costs nothing, you won't miss any groundbreaking discoveries, and you'll be helping me out too. Thank you so much, everyone. Black holes keep turning our understanding of physics upside down. But what if I told you that we might already be inside a black hole? Science has found astonishing evidence of this using the James Webb Space Telescope. Scientists have noticed that the majority of galaxies observed so far rotate in the same direction. About 2/3 rotate clockwise, while the other third rotates counterclockwise. In a random universe, however, the ratio would have to be 50-50. This observation of 263 galaxies was made as part of the James Webb Space Telescope Advanced Deep Extragalactic Survey, or JADES for short. And one possible explanation for this strange cosmic choreography is that our universe was born with a rotation, and that in turn would align with a theory called black hole cosmology. Put simply, our universe could be inside a black hole. What does that mean? Well, black hole cosmology is a super exciting theory that suggests our observable universe is inside a black hole, which in turn exists within a larger parent universe. The theory suggests that the event horizon, the boundary beyond which nothing can escape a black hole, is also the horizon of the visible universe. And it gets even crazier. This theory also implies that every black hole in our universe could be a gateway to another baby universe. These universes would be unobservable to us because they lie behind the event horizon. This means that information can never travel from inside a black hole to an external observer. Nikodem Poplawski, a Polish physicist at the University of New Haven, is a strong advocate of this theory. He says, "The matter inside the black hole reaches a state of finite, extremely high density, stops collapsing, experiences a recoil like a compressed spring, and begins to expand rapidly. Extremely strong gravitational forces near this state cause intense particle production, thereby increasing the mass inside a black hole by many orders of magnitude and amplifying the gravitational repulsion that drives the recoil." And this rapid recoil following such a massive impact could be what led to our expanding universe, an event we now call the Big Bang. Black holes are, after all, masters of gravity, and perhaps it was a kind of gravitational recoil that caused our universe to begin within the event horizon with the Big Bang. But what does this have to do with the rotation of galaxies? Lior Shamir, lead author of the new study, explains the analysis of the galaxies was conducted through a quantitative analysis of their shape. However, no special skills or knowledge are required to recognize that the numbers are different. With the power of the James Webb Telescope, anyone can see it. Here you can see the James Webb image. The galaxies are color-coded according to their direction of rotation. And indeed, we see a clear rotational trend. Black holes that form from stars or at the centers of galaxies all rotate. This means that the axis of rotation of a black hole would influence our universe if we were inside that black hole. So-called space-time torsion may have helped prevent a singularity, an infinitely dense point with no volume, and instead created a new self-contained universe. If our universe inherited the rotational axis of the parent black hole, this could have influenced the motion of galaxies and explain why the majority of galaxies rotate in one direction. What we call the universe could be just one of potentially infinite bubbles in a much larger multiverse. Every black hole in our universe is a portal to another universe, and our own universe could have emerged from the black hole of a parent universe. There is an argument that, in my view, strongly supports this theory. The mass of our universe and its size fit surprisingly well with what one would expect from the event horizon of a black hole of this dimension. If you calculate how large the Schwarzschild radius of a black hole with the mass of the universe would be, you arrive at just under 45 billion light years. So pretty much exactly the radius of the observable universe. Our universe has exactly the dimensions one would expect from a black hole of this mass. Could that be a coincidence? Still, of course, it must be said that all of this is speculative. Black hole cosmology is a fascinating theory, but for now it remains just that, a theory. If our universe does indeed exist inside a black hole, then we must also discuss the gigantic dimensions that such cosmic monsters can reach. Supermassive black holes are among the most fascinating objects in the cosmos. In the so-called Phoenix Cluster, a monster has been discovered that defies our imagination. The Phoenix Cluster is a massive and hot cluster of galaxies located about 8.5 billion light-years from Earth, and it is believed that the very same supermassive black hole at the center of the Phoenix Cluster is responsible for the formation of so many stars there. The black hole absorbs material from its surroundings, thereby releasing energy and radiation that help gas and dust near the black hole clump together and eventually form stars. In addition, there are gigantic amounts of hot gas at the center of the cluster. This gas has a temperature of several million degrees and emits radiation in the X-ray spectrum. Here you can see an X-ray image from NASA's Chandra Space Telescope. The black hole is also responsible for these high temperatures, as it releases heat and radiation that heat the gas. This energy is primarily ejected in the form of gigantic jets, violent explosions that originate in a black hole's accretion disk. This monster goes by the name of Phoenix A. According to estimates, and now hold on to your hats, it weighs about 100 billion times as much as the Sun. With 100 billion solar masses, this cosmic behemoth is thus another 34 billion solar masses heavier than the previous record holder, Ton 618. Here we see a size comparison between Ton, Phoenix A, and Neptune's orbit. So Phoenix A is truly a gravitational monster, and here are some more incredible facts that will blow your mind. Phoenix A is a whopping 24,000 times heavier than the central black hole of our Milky Way Sagittarius A star. It would take 71 days and 14 hours to orbit Phoenix A once, traveling at the speed of light. Using the Hubble telescope, NASA was able to capture an even better image of the active core of the Phoenix cluster. The thought that we're looking at something 8.5 billion light-years away is simply incredible. A NASA statement regarding the image reads, 10 billion solar masses of cool gas are located along filaments north and south of the black hole, likely originating from outbursts of the supermassive black hole at the center of the image. With these unimaginable dimensions, Phoenix A belongs to a very special group of black holes known as stupendously large black holes, or SLABS for short. This term describes black holes that are significantly larger than ordinary supermassive black holes. Phoenix A is the only known SLAB to date, and now some researchers are already speculating that somewhere out there, in the vastness of the cosmos, there could even be black holes that accumulated so much matter shortly after the Big Bang that they could weigh up to 100 trillion times as much as the Sun. But what would actually happen if a black hole like Phoenix A were near us? Here you can see our beautiful Earth unsuspectingly orbiting the Sun. And now let's place a black hole next to the solar system, increasing its mass to 100 billion solar masses. Well, that doesn't seem to sit too well with the solar system. All celestial bodies, including the Sun, disappear behind the gravitational maw. Incidentally, an effect called gravitational lensing was also clearly visible here. The gravity of many black holes is so strong that it influences the light particles traveling from the cosmos into our eyes. This results in the bizarre distortions we just saw here. And astronomers can even take advantage of this, since we can use black holes to see into areas of the cosmos that we wouldn't be able to see without their gravitational lensing. These dimensions are really hard to grasp, but black holes are impressive not only because of their sheer size, but also because of their behavior. Some of them race through space completely out of control. NASA has discovered a particularly spectacular example using the Hubble telescope. The image showed a kind of bright streak. Peter Van Dokkum initially thought this was a so-called artifact in the image caused by cosmic radiation. In other words, something you'd normally want to remove from the image, but when the research team filtered out the image artifacts, the streak was still visible. Little by little, it became clear. What was initially thought to be an image error is one of the most exciting discoveries in a long time. A supermassive black hole ejected from its galaxy, trailing a tail of newly forming stars behind it. This fleeing black hole likely has a mass of about 20 million suns. That makes it more than 4 times heavier than the central black hole of our galaxy. Now the question arises, can we reconstruct the sequence of events? Here, the black hole was clearly ejected from its galaxy by a collision, and Professor Dokkum's team assumes that a truly rare and bizarre triple collision occurred, because when two black holes collide, they usually merge into an even heavier black hole. But when 3 black holes collide, one of them can be ejected. But where does the trail of young stars that the black hole leaves behind come from? As the black hole was being flung out of the galaxy, it naturally tore out a great deal of gas, and it also moved through through the hydrogen-rich outer regions of the galaxy, the so-called halo. Naturally, a lot of gas was sucked into the black hole's gravitational maw, but due to the immense speed, large areas of hydrogen were also simply compressed by the black hole as it raced past. And if you compress enough hydrogen, you get a star. The band of stars that the black hole drags behind it stretches over 200,000 light years. That makes it about as large as our entire galaxy, the Milky Way. So black holes don't just have a destructive effect, they are also the creators of new suns. The entire event took place at a distance of 7.5 billion light years. So this black hole will not come anywhere near our solar system. But knowing that black holes are out there, roaming about, can naturally be a little unsettling. But black holes have even more surprises in store. What if they didn't just destroy matter, but could also serve as gateways to other universes? Even if we could travel at the speed of light, it would take us 200,000 years just to reach the edge of our galaxy. Does that mean interstellar travel is impossible? Every Star Trek fan knows we simply have to warp space. Albert Einstein was the first to grasp the concept of space-time. We are surrounded by space and time, dimensions that are inseparably linked, but do not appear directly visible to us. Mass influences space-time. What we perceive as the normal state of space-time is space-time, under the influence of, above all, the Earth and the Sun. But wouldn't it also be possible to essentially fold space to connect 2 points directly? That would be a wormhole, also known as an Einstein-Rosen bridge. This would, of course, drastically shorten any journey, and we could instantly travel to any destination in the universe. That is a wormhole. But doesn't that violate the laws of physics, which state that nothing can travel faster than light? No, because we don't move faster than light through a wormhole. Our destination has simply moved closer to us because the space in between has been folded away. Wormholes therefore do not violate the theory of relativity and are fully consistent with the laws of physics. The only little problem is that we've never actually found a wormhole yet. But in a research paper, a team of Bulgarian scientists makes a wild claim. According to them, we've already discovered wormholes long ago because black holes are actually wormholes. That would mean we're surrounded by wormholes, and that, for example, a supermassive wormhole lurks at the center of our Milky Way. The scientists have calculated that when viewed from Earth at small angles of inclination, wormholes would exhibit a polarization pattern very similar to that of a black hole. Depending on the perspective, a wormhole would therefore appear exactly like a black hole when observed with Earth-based telescopes. A wormhole's mouth would look exactly the same to us as the accretion disks that form around black holes. The exact same applies to Sagittarius A star, the central black hole of our galaxy. We have also observed it from an angle that would make it impossible to distinguish it from a wormhole. The realization that any black hole, based purely on its appearance and the properties we've observed, could also be a wormhole, and that we might therefore be surrounded by plenty of wormholes, is quite spectacular. But now the question remains, isn't there a way to distinguish between black holes and wormholes? After all, before venturing into such a monstrosity, it would be quite helpful to have that certainty. In fact, the researchers describe in their paper a way in which we can identify wormholes beyond a doubt. According to this, we would have to observe it from a less flat angle than the black holes we have seen so far, since this is the only way to make the differences in polarization clear. And for that, we'd need a whole lot of luck. If a very massive object was situated between us and a potential wormhole, that object would bend the light reaching us, allowing us to view the wormhole from a different angle. Through such a gravitational lens, we could perceive the subtle properties that might distinguish a wormhole from a black hole. Until we are lucky enough to catch a glimpse of a suitable gravitational lens or even a direct view, however, the truly exciting realization remains that, mathematically speaking, all black holes discovered so far could be wormholes. The wormhole theory leads us directly to another fascinating concept in physics: black holes. A brief recap of what has happened so far. According to most astrophysicists, our universe has existed for just under 13.8 billion years. The prevailing view is that it began with the Big Bang. All the energy and matter, the planets, nebulae, stars, charming YouTubers, and so on, was compressed into a tiny point. For mysterious reasons, this point then began to grow and grow until today. And today, of course, the universe has reached gigantic proportions and is filled with billions, if not trillions, of galaxies. And it is still expanding. The vast majority of galaxies are moving away from us at this very moment. That's the state of cosmological knowledge in a nutshell. But one question remains unanswered to this day. Why? Most astrophysicists say just because. The universe arose from nothing, and before the universe, there was simply nothing. But there's an idea that goes in a slightly different direction. Our universe is the product of a white hole. To understand this, however, we first need to clarify what a white hole actually is. You can think of it as the counterpart to a black hole. Put simply, black holes pull things in while white holes spit things out. While no physical force can escape beyond the event horizon of a black hole, not even light, the event horizon of a white hole could not overcome any external physical force, meaning you couldn't get in at all. And if we take this idea further, every black hole could be connected to a white hole. That would bring us back to our wormhole theory. Practical proof of the existence of white holes is still pending, but they are possible within the framework of Albert Einstein's famous field equations. And after all, those equations have already successfully predicted black holes. Another argument for the existence of white holes is the so-called information paradox. When something disappears behind the event horizon of a black hole and ultimately becomes part of the singularity, the information of the swallowed object is lost, except for its mass, electric charge, and angular momentum. You can't gather any more data about a black hole than that. But according to quantum physics, information can't actually be lost forever. The solution to this information paradox could be, that's right, white holes. The information might not be lost at all. Hidden from our prying eyes, it's simply regurgitated somewhere else from a white hole. Couldn't this principle of the black-white hole relationship also be perfectly applied to the entire universe? To understand this even better, we need to venture a bit into the realm of quantum physics, that mysterious branch of physics dealing with the tiniest elementary particles. After all, the principles of classical physics break down somewhat when it comes to singularities. Some quantum theories therefore quantify space-time and postulate a quantum theory of gravity. They conclude that classical physics' view of black holes and the like is incomplete. According to the theory, the fundamental building blocks of space-time take the form of extremely small quantum loops, and these loops have a finite, that is describable size. Let's imagine a very, very massive star on the verge of collapse. That is, it ends in a hypernova and compresses its residual mass to such an extent that a black hole is formed. According to quantum loop theory, this compression of the star cannot reach the point of singularity, that is, the point of infinite density. Instead, before reaching the point of singularity, the star would undergo a quantum leap. Once a certain pressure is exerted on the star's residual mass, the black hole transforms into a white hole. This process of transforming a black hole into a white hole would take only fractions of a second. And it is precisely this loop quantum leap of a dying star that could be the starting point of a new universe. Our universe could have come into being when a very heavy object collapsed somewhere else in a parent universe, creating a white hole through a quantum leap. Physicist Lee Smolens popularized this theory and describes it as follows: a star that collapses into a black hole is compressed very quickly to infinite density, and time stands still. Instead of collapsing to infinite density, the star collapses to a certain extreme density, then rebounds and begins to expand again. The point where time ends inside a black hole is connected to the point where time begins in a new universe during a Big Bang. It's mind-boggling. Black holes offer up so many theories that just thinking about them makes your head spin. I'll keep you updated on any further breakthroughs on this topic, so be sure to subscribe to the channel now so you don't miss out, and don't forget to hit that thumbs up. And now let's move on to another mystery of astronomy. Scientists have received several mysterious signals from the depths of space, and some are already suggesting that we may have received messages from an interstellar civilization. What's the deal with these cosmic signals? You'll find out in the video shown in the top right corner. Be sure to click on it, and if you click in the bottom left, you can check out my space shop for shirts from the Plush Planets videos and other nerdy stuff. Every order really supports my work. Otherwise, I'd say see you in the next video. Take care, everyone.